In this video, we're going to be doing a Unit 2 Forces banked curve problem where we have a road that is tilted and the outside edge is higher than the inside edge, allowing vehicles to turn safely at higher speeds. So for this problem, we are going to have a maximum banking angle at 66 degrees and the turning radius at 320 meters. So we want to know how fast a driver must go to make it around the curve without sliding up or down the ramp, and we're assuming that we have no friction present. Now, what we can do is first draw the force diagram. For this car that is on that angle, we can draw that object having an upward force here. So we have a normal force that is going to be perpendicular to that incline. And acting downward is our force of gravity. Acting towards the inside of that incline, we have Fn sine of theta. The reason is because down here, this angle we know is going to be our angle theta, which was 66 degrees. So again, let me mark. This was Fg. This is 66 degrees. If you know that is 66 degrees, then you know that this angle is also going to be 66 degrees because they're alternate interior angles. So then if you know that's 66 degrees, you also know that if you connect a triangle up here, this will also be equal to theta. If that's theta, then we can relate the sides using this side as Fn sine of theta, and then this sine will be Fn cosine of theta as your vertical component. So remember that for your normal force, Fny and Fnx, when you have Fnx, it doesn't necessarily have to be cosine just because you have the horizontal component of something. And just have the vertical component of something, it doesn't have to be sine. It's dependent on the trigonometric ratio. So now our dilemma is that when you have a banked curve, if you go too fast, then you're gonna go out and you're slipping. If you go too slow, you're gonna go into the center. So you have to find that perfect speed that allows you to stay up. Now, we're gonna choose our axes to be our x horizontal, and that horizontal is gonna be toward the center of the circular path as positive. Now, our vertical is gonna be upwards. Now, what we can see is we can apply Newton's second law vertically. Since we know that the car isn't going to be moving up and down through the ramp, we can say that our summation of forces in the vertical direction is equal to MAY. So because AY is equal to 0, then the summation of forces in the y direction is equal to 0, and we have a state of vertical equilibrium. So if we write out our forces, we have our normal force in the y direction minus the force of gravity. That's going to equal to 0. You can see that Fny is acting straight up. So that is how we see that those are acting at the same direction in the vertical direction, which is why we are able to subtract them like that. So if you substitute that into our expression, we know that Fny is equal to Fn cosine of theta, and Fg is equal to mg. That's also equal to 0. So if you add mg to both sides, you get that Fn cosine of theta is equal to the mass times the gravity. If we solve for Fn, then we get Fn is equal to mg divided by cosine of theta. Now, what we can do is apply Newton's second law horizontally. The summation of the forces in the horizontal direction is equal to the mass times acceleration in the horizontal direction. We know that when you have circular motion, your acceleration in the horizontal direction is equal to AC, which is equal to v squared divided by r. So then we have ax in our equation, correct? So we can just substitute ax for this entire expression here. So this is going to be the summation of forces in the horizontal direction is equal to the mass times velocity squared divided by r. Now we know that the only horizontal force in our diagram is going to be the horizontal component of the normal force. So this is our only force here. Now we can set that equal to this side. That is going to be Fn sine of theta is equal to mv squared over r. Now what we can do is we can substitute in the expression for normal force. From our vertical equation, we got Fn is equal to mg cosine of theta. We have that same Fn expression over here. So you can take your normal force and then you substitute it in there. Now after this, you can cancel the mass on both sides. So you're ending up with g sine of theta divided by cosine of theta is equal to v squared over r. So then you can take sine theta over cosine theta and recognize that that is a trigonometric identity, tan theta. So then we can substitute this into our expression. We have g times tan theta is equal to v squared over r. You can multiply both sides by r. You get rg tangent of theta is equal to v squared. You take the root of both sides, and you get that v is equal to the root of rg tangent of theta. So this is the formula for a frictionless banked curve. Now we have numbers for this problem. Our numbers are going to be that r is 320 meters and our theta is 66 degrees. Additionally, gravity is 9.8 meters per second squared. So if we take that information, plug it into v here, we can find our speed. So that's going to be 320 times 9.8 times tangent of the angle 66 degrees. This is going to give us a speed of 84 meters per second, approximately. So on a frictionless banked curve, what we saw was that our vertical component of the normal force is going to balance the car's weight, and the horizontal component of the normal force is going to provide exactly the centripetal force that we need to term.